Hi, this is Jake Boringer, and in this video we are going to solve problem number 56 from the first electricity chapter. Here are the initial conditions. An electron is moving to the right with speed v0, and it's in an electric field also directed to the right. There's two parts to this problem, and the first part asks, what distance will the electron travel before stopping? So the reason the electron is going to stop is because electrons move in the opposite direction as electric fields. The electron has an initial speed to the right, but the electric field will start accelerating it to the left, as seen by the force diagram. We can use a kinematic equation to find the distance that the electron will travel, but first we need to know the acceleration. We can use Newton's second law, A equals F over m, and in this case F is equal to EQ, the force from an electric field, and then we substitute the magnitude of the electric field, which was given initially, and the charge and mass of an electron. We can now use v squared equals v0 squared plus 2a delta x to find the distance that the electron is going to travel before stopping. We can rearrange the terms in the equation and then substitute 0 for v final because the electron is going to stop, and then substitute v0, which was given initially, and then use the acceleration that we just found. Because the electron is going to accelerate to the left, we need to put a negative sign in front of the acceleration value. Accurate to 3 decimal places, that simplifies to 0.189 meters. It will be helpful to store the precise versions of delta x and acceleration in our calculator because we're going to use them later in part B. Part B asks how much time passes before the electron returns to its original position. So what's happening here is, you can see in the diagram, the electron has an initial speed v0 to the right, but with the electric field it starts to accelerate to the left. So it moves to the right at first, and then comes to rest momentarily, and then the acceleration eventually gets the electron's speed going to the left. So it starts to pick up speed from 0 and go to the left. So the electron eventually starts heading back toward the position that it originally started at. To find the time that passes before the electron returns to its original position, we have to use two separate instances of kinematics. It's similar to a problem where a ball is thrown in the air and then accelerates back down to the ground, because you can't use one equation to describe the entire trip. You have to just analyze the trip upward and then analyze the trip downward. For the first span of time, we're going to use v equals v0 plus at because we know the initial speed, and v final is 0 because the electron will come to rest and then start accelerating the other way. And the acceleration in this situation is constant. It's always the value that we found in part A. And again, it's going to be negative because the electron is accelerating to the left. Rearranging the equation and substituting the values, we can find that the first span of time is 1.37 times 10 to the negative 8 seconds. Now we're going to look at the amount of time it takes the electron to move from that point where its speed is 0 and go back to its original position. In this case, the electron is going to be traveling the distance that we found in part A, the distance that it took the electron to stop, but in this case it's going to be the negative distance because we want to know what time the electron goes back the distance that it came. We're going to use delta x equals v0 times t plus 1/2 at squared. Substituting our value for delta x, we use 1.89, but negative 1.89. The initial speed is 0, and the acceleration is still the value that we found from part A, and again it's going to be negative. This value for time also turns out to be 1.37 times 10 to the negative 8 seconds. And to find the total time that it took the electron to start at its original position, move out to the right, and be accelerated back to the left, That total amount of time to go back to its original position is the sum of the two time spans that we found, and that sum is 2.75 times 10 to the negative 8 seconds.